The next example is optimal binary search tree, or say OBST. Although it looks like a completely different problem, the solving strategy is basically the same, just as we had for the matrix multiplication problem. The OBST is the best for static searching. Static searching means there's no insertion nor deletion. But hey, don't we have binary search already? Well, say binary search actually corresponds to a perfectly balanced binary search tree, right? The root is the element at the middle position, and we have almost equal sized left and right subtrees, and it works well. But when we use binary search, we're actually assuming that every node is visited with the same probability. There's no difference. They're going to be visited with the same frequency. But that is not true in many cases, right? For example, when we write a program, we probably use keywords like for, if, else more often than we use main, right? The name of the main function will be used, say, once only. So the keywords in the compiler's dictionary are visited with different probabilities. And that's why we have this OBST. And the task of OBST is that given n keywords, and we assume that they are given in sorted order, and the probability of searching for each word is also given as p sub I. All right, so each word has a different probability of being searched. And we're supposed to arrange these words in a binary search tree in a way that minimizes the expected total access time. Expected total access time is defined as this. So here, d sub I is the depth of the ith word. 1 plus d gives what? Gives the search time for this word. Well, we're looking for this word. It's going to take us 1 plus d sub I number of comparisons before we can find this word. All right? If all the probabilities are the same, like 1 over n for every word, then this is going to be the normal average, right? It will be the total sum over n. That's the normal average of access time. And since each word might have a different probability, it's called the expected total access time. So our task is to minimize this number. Now, let's take a look at one specific example. Say, given the following keywords: break, case, char, do, return, switch, and void. Okay, and these are their probabilities. Now, here comes your first discussion question. Please draw the trees obtained by greedy methods and by AVL rotations, and at meantime compute their expected total access time. So greedy means we're supposed to be greedy on their probabilities. So for example, return is the keyword that has the largest probability of being visited, and therefore we would like to put return as the root. So it's going to take least time to access return. So being greedy means we can sort those keywords according to their probabilities and make insertions in that order. And that's the greedy method. And AVL rotations is that we simply make insertions in the given order and keep making AVL rotations to maintain a perfectly balanced tree. All right, so now click to pause the video, and I guess it's going to take you 10 to 15 minutes to draw the trees and do the computation. Okay, now let's compare our answers. This is the tree obtained by greedy method. So it's like we first insert return, so return will be the root. And next, we're gonna insert break. So here is break. And next will be char. And char will be here. Because let's keep in mind that this is supposed to be a binary search tree. So this is the tree obtained by greedy method. The total access time would be 2.43. Did you get it right? The next is the AVL tree. Okay, so this is the AVL tree we obtained. The tree looks quite balanced. However, the access time is actually worse than this one. It's 2.7. The optimal tree looks like this. And the optimal time is 2.15. You see that the problem with greedy method is that it's good to take the probability into consideration. However, since we have to maintain a binary search tree, we see some of the keywords with large probability, relatively larger probability, will have to be stored in a deeper position. And therefore, the overall performance is not so good. And the AVL tree is worse because it only considered the height of the tree, but totally ignored the probability. And therefore, the words with larger probabilities like return and break are pushed down to the deepest position. And that's why it's so bad. All right? Now, of course, the question is, how are we supposed to obtain a tree like this? Let's see. The idea of solving this problem is very much similar to the idea of how we solve the matrix multiplication problem. So step one is we must define a proper subproblem. Like the whole problem is to construct the tree for all the keywords from word 1 to word n. The subproblem is then defined to be constructing the tree for a subset of the words. It's very much similar to the way we define the subproblem for the matrices, right? We're supposed to find the total product from m sub 1 to m sub n. The first thing we do is to define the subproblem as the product from m sub I to m sub j, right? So it's just similar to that. And with this subproblem defined, we denote the cost to be c sub ij, and when I equals j, we define that cost to be 0. Okay, and the root of this tree is defined to be r sub ij, and another term, w sub ij, is the weight of this tree. And the weight of this tree is defined to be the total sum of the probabilities only. Okay, we have this term for some reason, and we're going to see next. Right, so our task is to find t sub 1n, the tree that is constructed for all the words from the first one to the last one, with this root, this weight, and this cost. So what are we supposed to do now? Think about in the previous example, what did we do at this point? We begin to think recursively with the idea of divide and conquer, right? And break this subproblem into two smaller sized subproblems, right? So here we go. For this tree, we can always pick up one word as the root, and this root will break the problem into two parts, and the left hand side forms its left subtree and the right hand side forms its right subtree, and therefore we can obtain a recurrence equation of the solution of this subtree and the solutions of its left and right subtrees, right? So what is c sub ij? It's the cost of the root plus the cost of its left subtree and its right subtree. So first of all, we're going to have this p sub k, that is the cost for the root, right? it's the probability times 1 because the depth of root is considered to be 0. So this is the cost for the root plus the cost of its left subtree and its right subtree. But is it all? Be careful here, because when we add this subtree into this tree, every word will have one extra level than what they have in this subtree, right? For example, the root of this tree will have depth 0 in its own tree, but when we put this subtree into this tree, the root will have depth 1. There's going to be one extra search time for each word in the subtrees, right? And that 1 corresponds to, we have to multiply that 1 with their probabilities. So that corresponds to the weights. All right, to rewrite them with those notations, we have that this is P sub k and this is C sub I to k minus 1. And this is C sub k plus 1 to j. And so for the weights, right? And the sum of these two weights plus this P sub k will be the total weight of this tree, right? So we combine these three terms into W sub ij, and therefore obtain a recurrence equation like this. But this is only for one fixed k. And our task is to minimize this cost, right? So in order to minimize this cost, what should we do? Similar to what we have done in the previous example, we just let k move from left to right to try all possible k's, right? And to find the smallest possible value. And therefore, we have this recurrence equation. If this tree is optimal, then we must pick up that root so that the optimal cost must be the smallest sum when this L goes from I plus 1 to j. And if this is the optimal solution to this problem, then these are also the optimal solutions to the smaller sized subproblems. So you see, everything is just similar to the previous example. Since this weight has nothing to do with this L, so it's a fixed number. So what is key is the sum of these two optimal solutions of smaller sized subproblems, right? So the key is, again, we start from the smallest cases and then increment the size one by one to obtain the solutions of larger and larger subproblems, and eventually you can obtain the final solution from 1 to n. Well, I guess it's still quite abstract. Now let's take a look at this specific example and let's see how we obtain that optimal tree step by step. All right, so this is the formula, and we're going to need a table and start from recording the results of the smallest size problem, which is the problem that contains only one word, from break to break, from case to case, and so on and so forth. And here we put the optimal root at this position. Since there's only one node, and obviously that node will be the only root. 0.22 is the current cost for this subtree, and when there's only one word, it's just equal to the probability. So this is the simplest case that we should start with. Next, let's increment the size of the problem by 1. That means we're going to construct those optimal trees with 2 words. All right, so first, let's try break and case. So now let's see how it works with the subproblem from break to case. So here we have 2 options. Option 1 is to take break as the root, and the other one is to take case as the root. But before we do anything, first let's calculate the total weight of this tree. The weight of this tree is simply the sum of their probabilities. So add them up, we get, this is 0.22 plus 0.18, that is 0.40. Okay, so this is the total weight. If we take break as the root, then the tree is going to be like this, right? So break is the root and case is its right subtree. So what is the cost of this subtree? Since this is a tree of only one node, the cost is given here. It's 0.18. And the other option is to take case as the root and break as its left subtree. So the cost of this subtree is here. Okay, in the table is 0.22. Alright, since the weight is fixed, we only have to pick up the smaller one between these two costs, which is this one. Okay, so we know that for this subproblem, the optimal solution would be this weight plus this cost. And the optimal root of this subtree is break. So let's fill in these two blanks. Okay, the first one is the optimal cost, which is 0.4 plus 0.18. That's 0.58. And the root is break. Alright, now we obtain that the optimal root is break and the optimal cost is 0.58. And similarly, we can obtain the solutions from case to char, from char to do, from do to return, and so on and so forth. So each sub-problem has a size 2, contains 2 words. Alright, now let's increment the size by 1 again. And therefore, we're supposed to consider the sub-problems of size 3, contains 3 words. So the first problem is what? Is from break to char. It consists of 3 words, break, case, and char. Alright, now let's try to find the optimal tree. Okay, now let's check out this from break to char. In this case, we have 3 different possible trees, right? The first one is take break as the root. Then we're going to have its right subtree with case and char, right? And another one is we take case as the root, and then we have break and char. And the third one is to take char as the root, and therefore we're going to have its left subtree with break and case. Alright, first of all, the total weight. The total weight is supposed to be what? 0.22 plus 0.18 plus 0.20, which is 0.60, right? Okay, so when we're calculating the optimal solution of this tree, since it has no left child, we only need the optimal solution of its right child. But here, do we have to recursively calculate the optimal solution of this one? Not necessary. We can just look up at the table, right? This is the subtree contains case and char. So the solution is already recorded here. It's 0.56. So here we have the cost being 0.56. All right. And for this case, we're going to sum up the optimal solutions of these 2 subtrees, which is the sum of these 2 subtrees. So that's 0.22 plus 0.20. That gives 0.42. Okay, now this one we only have to calculate the cost of its left subtree, which contains break and case, and that is one we have just obtained. It's here, 0.58, right? So the cost here is 0.58. So the optimal solution is the smallest one, which is this one, all right? So the optimal cost will be the sum of the total weight plus this cost. Altogether, I get 1.02. So let's fill in 1.02 here. And case is the root of this optimal structure. So let's fill in case here. Okay, so the conclusion is that case will be the optimal root, and the optimal cost is 1.02. Now I hope that you can complete the rest of the table by yourselves, right? Okay, so here we go. And finally, we have the solution from break to void, from break to void. And the optimal tree root is char, and the optimal cost is 2.15. Now it's time to reconstruct this optimal tree. So from this unit, we can see that char is the root of this final result. All right. Then let's check the input. This is the position for char, and char will divide the problem into two parts, where its left subtree contains break and case, and its right subtree contains from do to void, right? Okay, what we do next is we look at this table and search for the result from break to case. From break to case. Here, we know that the optimal solution for this subproblem is that break is going to be the root. So we have break as the root. Here we see that since break is the first word, it has no left subtree, and case will be its right subtree. We look at the unit contains from case to case. So case is the root, and case is its right subtree. All right? Now you can obtain its right subtree all by yourselves, right? So we search in this table for the subproblem from do to void. From do to void. And know that return is going to be the root. So here's return. Okay? And for this subproblem from do to void, since return is the root, its left subtree must be the subproblem from do to do. So here, do is the root of its left subtree, and its right subtree contains from switch to void. From switch to void. So void will be the optimal root. And finally, switch will be its left subtree, and that gives the structure of the optimal tree. And obviously, the total time complexity is big O of n cubed. But this is not the fastest algorithm. There's another one which can run in n squared time, and that's given in your textbook. So go ahead and check it out after the class.